Hey, Dirac Labs, Sam here. So in this video I'm going to show you how to solve the Dirac equation for the one electron atom. And the hydrogen atom is the most famous one electron atom, so I'm going to put that in the video title. So obviously we start with the U1 gauge covariant Dirac equation, made gauge covariant with by replacing the partial derivative with the electromagnetic gauge covariant derivative. And since this is the hydrogen atom problem, we need to use the Coulomb potential. So plugging that in, we get that for the Dirac equation. Now it's the case usually that this problem is done using the alpha and beta matrices that Dirac originally used when writing the when he first published the Dirac equation instead of the gamma matrices. And I think the reason why is to get the matrix off of the time derivative term, because we're looking for energy eigenvalues. But I could be mistaken. However, it's regardless of why, that is how it's usually done. So that's how I did it here. So if we multiply the whole equation by beta, then we get the old form. Now the next thing I did was I multiplied the IH bar in and also multiplied it by C to get this form of the energy operator here. And then I recognized that we're looking for energy eigenfunctions. So the operator just gets replaced with the eigenvalue there. Okay, so then the next thing that I did was I got this rewritten so that the form of the momentum operator is obvious, and then I rewrote the Dirac equation symbolizing the momentum operator just with a p. Now this is where we need to coordinate transform the equation. The potential term is already in spherical coordinates, but the rest is not in spherical coordinates yet. This term and that term don't change under the coordinate transformation, but that does. So we need to work out what alpha dot p is in spherical coordinates. And this is where the heuristic method for getting the Dirac equation in spherical coordinates comes in. Now let me explain what I mean by that. Typically when you coordinate transform something, you start with the generally covariant version of that, and then you just pick the coordinate system. And there is a generally covariant Dirac equation, and I've used it in previous videos. In fact, I even have a video on writing the Dirac equation in spherical coordinates, where I start with the generally covariant Dirac equation and get the result that way. However, the generally covariant Dirac equation, introducing that requires introducing a bunch of concepts like gauging the Lorentz group and spin connections and tetrads and curved gamma matrices, and it's quite a bit of an advanced math thing. So typically when they show you the Dirac equation for the hydrogen atom, it's at a level that's not advanced enough for that, and also usually this is the only problem where you need the Dirac equation, at least at that level, where you need the Dirac equation in spherical coordinates. So if they're only going to coordinate transform it once, and it's at a level really too low to introduce the generally covariant Dirac equation anyway, it makes it very favorable for a heuristic method to be found just for the coordinate transformation to spherical coordinates for the hydrogen atom problem. So alpha dot p is the thing we need to coordinate transform, and I'm going to show you the heuristic way that's typically used for writing the Dirac equation in spherical coordinates as I just explained. And it starts with this quantity here, this triple product. We rewrite it in two different ways, set them equal to each other, and then do some solving, and you'll see how that works out. The first way we want to evaluate this quantity is by combining these first two terms. So we see if we write them out explicitly in Cartesian coordinates, where it's really easy to do that, where it's really obvious to do that, or obvious how to do that, then we get this. So if I then multiply that through, we get this. And I've also rearranged the terms. I brought some terms out front here. Now alpha matrices square to 1, so then, or square to the identity, so then we get this. And then this just ends up equaling r squared. The rest of the terms are kind of interesting because what we can do is we can pair them up so that the only thing different between the two is the order that the alpha matrices appear in. So then we can anti-commute them because they anti-commute, so we can commute them but then put a minus sign on it. So then every term has a copy but with the opposite sign, so it cancels and simplifies down to this result, which is just r squared times that third factor there. And so we get the first key result. This is the first way of evaluating it that we need in this box there. Now there's a second way of evaluating it that's trickier that we also need. So let's go through that. Now this requires us to combine these two factors here in kind of a tricky way. So the first thing I did was I wrote them out in Cartesian coordinates where it's easy to do that, and then I multiplied it out. Now alpha matrices square to the identity, as I said, so that gives us these three factors here, which is just the explicitly written out version of alpha, r dot p, not alpha anything, just r dot p. So then we've got to figure out what these other terms end up being. Now, what we can find, we can pair these terms up such that they contain the same alpha matrices, but they're in the opposite order, and then they anti-commute, so we can change the order at the cost of a minus sign. The x and the component, or the component of r and the component of p that's in there are not the same though, so it doesn't cancel like it did last time. But you do get something here that looks like a cross product. In fact, it looks a bit like the components of r cross p. In fact, that's exactly what it is, and that's going to end up being what it turns out to be. But we need to do some additional things with these alpha matrices. So the first thing that I did, and you'll see why I did this later, but I multiplied these terms in the large parentheses after the r dot p by minus I, and then I also multiplied it by I to compensate, so I wasn't actually changing the value of the expression. Now, okay, so the next step here is to take the terms that were in the last version we had and split each one into two terms. So instead of just this term right here, we have 1/2 it, but then we have another copy of 1/2, so it adds together, the halves go away, and you end up where you were before. But we need this. We need it this way. We need it written this way, and you'll see why. So the next thing that we can do is we can recognize that the alpha matrices anti-commute, and we can anti-commute them in a manner that forms a commutator here. We can pair terms together and anti-commute some of the alpha matrices off in front of one of the pairs such that it forms a nice commutator. However, we know that the commutator of the alpha matrices, or rather minus I over 2 times the commutator of the alpha matrices, gives you components of this sigma vector that shows up in Dirac Equation mathematics a lot. But the thing is this is the x component, and then this is the x component of r cross p. This is the y component of sigma, and then this is the y component of r cross p, and then the z component. Clearly, it's just I sigma dotted with r cross p, and that's exactly what it is. So then we get this critical result here. However, r cross p is just the angular momentum operator, so we have that there. And we had that other result that we got by evaluating this triple product in a different way, and we can equate the two. Then we can take the radial component of the momentum operator, which unsurprisingly gives you this, or rather just expanding out the whole dot product. It gives you this without the r factor. That's the radial component of the momentum. So the r factor comes from the r and the dot product there. Okay, and then we can also write this dot product here as the radial component of the alpha matrix vector times r. Okay, so the next thing that we have to do, the radial part of this derivative is not manifestly Hermitian. It isn't Hermitian, the radial part specifically, and we want the radial part to be manifestly Hermitian. So we need to invent an operator that is, and then manipulate this until it shows up, until that operator shows up. It turns out that this operator here is Hermitian. And in terms of derivatives, of course, it ends up working out to be like that trivially. And then we can rewrite it in a really beautiful way like that. So we have this PR that is not the radial component of the momentum or operator, that is manifestly Hermitian and evaluates like that, or has this value. So then we need to figure out how to get that in there, in our expression, so the radial part is manifestly Hermitian. It'll make the problem easier. And to really see that, you just have to do it without doing this. It's just experience that tells you this is the better way to do it. Okay, so how do we get that in our expression? Well, let's start by adding and subtracting IH bar. And then let's put the added IH bar right there. And then let's factor out the minus IH bar from this. And then let's also factor out an R. So then we get that. However, that's minus IH bar ultimately times this times the thing in the parentheses there. So it's just PR. So we've figured out how to work it in. So then just writing that out, we have this way of writing the r squared alpha dot p operator in spherical coordinates in a very convenient, elegant way. So we're almost done with the coordinate transformation. Remember, the thing we actually wanted was alpha dot p. So then we just divide by r squared and we get alpha dot p. We just divide by r squared and then we get alpha dot p expressed in spherical coordinates in a very convenient way. So then now the Dirac equation in spherical coordinates becomes... Oh wait, shoot, I forgot I printed double-sided. That's skipping way ahead. Sorry, just a moment. Okay, so yes, that makes more sense. This is more what I remember from doing the calculation. Sorry about that. Okay, so then, yeah, dividing by r squared ultimately gives us this result for alpha dot p in spherical coordinates. So this is the result that we want. That's the result that we need. And then inserting that into the Dirac equation, we get this. Okay. Yeah, the Dirac equation I pointed to when I was on the wrong page a minute ago actually was a few steps ahead, and it had eigenvalues replacing the angular part. Okay, so now the next step in this problem is the next step in this problem is to study the angular part of the alpha dot p operator, which is this thing right here. It's worth rewriting this operator in different ways to reveal its action on the wave function, and we find that it has these eigenvalues, which I just summarized as k, where the j operator is the sum of the orbital and the spin angular momentum operators. Okay, so because the operators are applied to the wave function, that is an eigenfunction of these operators, well, specifically it's an eigenfunction of that operator, and it's an eigenfunction of the square of those operators, specifically. Something can't be a simultaneous eigenfunction of every component of an angular momentum operator, of course. But anyway, you know what I mean. Because the operators are applied to a wave function that is an eigenfunction of these operators, the operators and their eigenvalues were freely interchanged in the above sequence of manipulations. So now that we've worked out the eigenvalues of this, actually, given the nature of the beta matrix, of course it's not going to change them. The eigenvalues of this operator, which commutes with the Hamiltonian, are actually given here. Now it's important that it commute with the Hamiltonian because, given that it commutes, the hydrogen atom eigenstates will be eigenstates of this operator, and will therefore be will additionally be indexed by quantum numbers associated with this angular operator's eigenvalues. This allows for the next step in the hydrogen atom problem, and that's studying the radial equation. So we'll postpone the rest of the angular part. The reason why we studied the angular operator here was to get the eigenvalues and to ultimately get an operator that commutes with the Hamiltonian, a version of the angular operator that commutes with the Hamiltonian. So then the eigenvalues of that operator can be used to index the states. So then we can write the Dirac equation in terms of that operator, and then replace the angular part with the eigenvalues of this angular operator that commutes with the Hamiltonian. We can replace it with its eigenvalues and then just get the radial equation. So, of course, beta squared is just the identity, so we can stick 2 betas in there and combine one with this k operator. Okay, now we're at the Dirac equation. And then we can just recognize that the k operator will apply to the wave function to give the eigenvalues. And then that gives us this. Now we can separate variables because there are no angular derivatives, so we postulate the wave function breaks up like that, and then that gives us our radial equation. So now we can start attacking the radial equation, which is the longest part of this process, and then we'll come back and we'll look at that angular operator again that we just replaced with the eigenvalues to get the radial equation. We'll look at that again after we've attacked the radial equation, because once we've attacked, and we'll get the angular part of the solution, we'll get the eigenfunctions of that operator, and then we'll combine it with the radial solution that we got, and we'll have the complete solution to the Dirac equation. Also, just like in the Klein-Gordon and Schrödinger case, the energy eigenvalues come from the radial part of the problem. Okay, so to go further with this equation, one must pick a specific representation of alpha r and beta. The ordinary Dirac representation could be used, but there is an easier option. Because this equation contains only 2 different matrices, there are enough linearly independent 2x2 matrices that satisfy all the required properties to be Dirac matrices for a 2x2 representation to be possible. Where the properties required to be Dirac matrices is that they square to the identity and anti-commute with each other. One can therefore make the solving process a lot easier by selecting a convenient 2x2 representation instead of instead of the 4-dimensional Dirac representation. At the end of the calculation, one can then transform back to the Dirac representation once we've solved it in the 2x2 representation. In selecting a 2x2 representation, the desired characteristics are that it makes the solving as easy as possible, and that it makes the positive and negative energy solutions easily distinguishable. Given these characteristics, the best representation is this 2x2 one there. Now, if you remember from the Schrödinger and Klein-Gordon equation version of these problems, of this hydrogen atom problem, we factored out a 1 over r in the first ansatz. This is no different. We do it here too. So if we insert this ansatz in those matrices, ultimately it gives us this set of 2 equations right there. Okay, so then, well, that 2-dimensional matrix equation, and then we get the set of 2 equations here. Now we can compute the asymptotic forms. So remember in the Klein-Gordon, the Schrödinger equation case, we calculated 2 asymptotic forms and then factored out the asymptotic behavior from the solution. And this is after we already factored out the 1 over r. And we ended up with something that could be described by a power series, and then we solved it with the power series method. The steps we're going to take here are exactly the same. They're just more complicated because it's a system of equations, and we're actually going to take them in a slightly different order. We're going to figure out the large R asymptotic form, factor that behavior out, plug it into the equations, and then take the small r limit of those and get another asymptotic form, and then plug the power series times that second asymptotic form in. So it's the same process, the same steps, essentially, it's just a different order. And this seems to be the way that this problem is usually done. I guess it's easier. I haven't tried it multiple different ways, but it should give the same answer, it just might not be as easy. So anyway, continuing with the way it's normally done, it's the same steps, but in a bit of a different order. So if we take the large R limit of those equations, then we get these equations, and we can solve for g in terms of derivative of f, and f in terms of a derivative of g, and then get second order equations which we can solve for asymptotic forms. Normalization considerations tells us to pick that one. So then we postulate this ansatz based on factoring out the asymptotic behavior, plugging it in. Ultimately we get this set of equations right here. Okay, so then we need to deal with those. Now for the small r behavior. So we take the limit of those equations as r goes to 0, and we are left with these equations here, and then we can manipulate them. We can do some substitution to get separate equations for f and g, and then we get these solutions here, and then normalization tells us to pick that particular asymptotic form. So then we factor that asymptotic behavior out and postulate that the remaining factor is a power series and insert that into these equations, the full equations, and we ultimately get this representation in terms of the coefficients, and it's the standard procedure where we plug it in, make all the powers on the rows match, and then set the coefficients equal to 0. So the next thing that we need to do is manipulate these a little bit. Ultimately, what the goal is to manipulate these equations such that we get a relation between the f coefficients and the g coefficients. And it turns out they're actually proportional here. This result is quite important. Now this equation and the previous boxed equations can be used to investigate the large A behavior of both series. First, wait, that's supposed to be A. I forgot to change J to A. Originally I was using J as the index, but then J is the total, is usually associated with the total angular momentum, so I changed it, but I guess I missed one. So that's supposed to be A. First, the large A limit must be taken of all the relevant equations. Now one can obtain relations giving the large A behavior of both. So once we have these relations, we can get large A limits for the recurrence relations. So we get these large A recurrence relations here. We haven't written out the totally general recurrence relations yet. We will later. But the totally general decoupled recurrence relations. But here we have the large A recurrence relations. And of course that gives us this result, which just tells us that it behaves like an exponential. In fact, when you sum the series to infinity, of course, we get an exponential, which is not normalizable. So then we throw that out and terminate the series. And terminating the series gives us energy quantization, as is usual. So we postulate some power at which it terminates, called A max, and then we say F, again, I forgot to stick the A's in there instead of J's. I apologize. It's not too confusing, I don't think. But anyway, so imagine that's an A, F of A max plus 1, and G sub A max plus 1 are both 0. So then we can take these relations. Let's see. Where did those come from? Oh yeah, and then we plug this condition into it. We plug this condition there into it, and it gives us these two relations. So this condition for termination plus these equations ultimately give us those results there. Okay, so with the last result, one obtains a useful condition for termination, which was, let me find it. that condition followed from that. I guess I referred to that as the condition of termination, whatever. This is us imposing termination, I guess, and this is the condition we get, or the conditions we get for the as a result of imposing termination, and that's what I was referring to when I said we get useful conditions of termination. So with this result that I mentioned earlier, combined with this one that we just got as the useful condition for termination that we got from just requiring that the series terminated after we realized that not doing that results in non-normalizable solutions, we get these two independent results for the ratios of f a max and g a max. And of course they have to be equal, so we set them equal to each other and we solve. Ultimately, when we plug everything in, all the values for the various constants, and solve for the energy, we get this result here. Well, I guess specifically we get this result, but then we pick the principal quantum number to have this value to give us the standard form solution, and then we get this final result. So now we have the energy eigenvalues. This is one of the main results here. This is one of the really key results here. This is sort of a big moment. It's the energy eigenvalues. It's one of the really important results in this problem. The two are the energy eigenvalues and the wave functions. Those are the important goals, and this is one of those. Okay, so now back to the wave function. The next step is to write out the explicit recursion relations for both positive and negative energy solutions, meaning both the F and the G series. Okay, so if you actually go back to the power series representation of the equation that we were trying to solve after we'd factored out all the asymptotic behavior, then you can ultimately solve it and get decoupled completely general recurrence relations, meaning we haven't simplified it in any way or taken any limits. So the general recurrence relations for the F series is that, where C and D are defined as I've typed up. So then, if we do the same for the G series, this is the result we get. It turns out that the polynomial solutions generated by these recurrence relations, well, specifically the polynomial solutions you get by terminating these, or the power series generated by these recurrence relations, can actually be expressed in terms of associated Laguerre polynomials. Specifically, the coefficients, or the series whose coefficients were denoted with F, that summed to give phi. So phi in terms of Laguerre functions is given like that. So this expression in terms of Laguerre functions generates the same polynomials that terminating the series generated by this recurrence relation generates. So that's why they're equivalent. And if you do the same thing for the G series to get the gamma polynomials, and where was the first time oh yeah, so just basically what you get when you terminate the phi and gamma series there, then you end up getting polynomials that are generated by this expression in terms of associated Laguerre functions. So then if we go back to the f of rho that we had, which was the second asymptotic form, the small r asymptotic form, times the polynomials, then this is what f of rho equals, and the same thing, if we do the same thing, we get this result for g of rho. And then if you remember, f of rho and g of rho had the large r asymptotic behavior factored out. So if you put that back in, then you get these capital F of rho and capital G of rho in terms of the two asymptotic forms and these associated Laguerre functions. So then if we remember that we factored out a 1 over r behavior, the full radial solution in this representation of the alpha r and beta matrices is this. So that's our radial solution. Now we need to transform back to the Dirac representation. Oh wait, actually, let's normalize first. I guess I normalized first. I forgot I normalized this first. So that was the unnormalized solution that I just showed you. If you follow the standard normalization procedure, then what you ultimately get for the normalization constant is this. So then the normalized radial solution in this two-dimensional representation is given by that. Now, if we do the transform back to the Dirac representation, so alpha r goes to that and beta goes to that, little changes. Really all we get is that there's a duplication of the functions because we're going to a four-component spinor, and these functions correspond to positive and negative energies. There are two positive and two negative energy components corresponding to the different spin states. The only other change is these factors of I on the f functions, and that's then the result in the Dirac basis. So it was, as you can see, much easier to solve it in that two-dimensional basis and then transform back at the end. The solution doesn't hardly change. So now that the radial part of the function is, or the wave function is completely determined, the angular part needs to be determined. As was established above, the angular part is the set of eigenfunctions of the k operator. L is the orbital angular momentum operator, so the eigenfunctions of this operator, meaning the k operator, must, among other things, function as standard orbital angular momentum eigenfunctions. From non-relativistic quantum mechanics, it's known that the standard orbital angular momentum eigenfunctions are just the normalized spherical harmonics, which I talked about in my video on solving the Schrödinger equation for the hydrogen atom and solving the Klein-Gordon equation for the hydrogen atom. And the sigma matrices are the operators corresponding to spin angular momentum for a spin half particle. So the eigenfunctions of the operator in question must also function as standard spin angular momentum eigenstates. The standard spin eigenstates are, of course, just these 2x2 vectors. This means that if one finds a four-component function that is a standard eigenstate of both spin and orbital angular momentum, then one has just found the eigenstates of the operator k, which is the desired result. However, if a state is an eigenstate of two different kinds of angular momentum, then it is an eigenstate with total angular momentum that is the sum of the two. Therefore, one must add, whereby add I mean angular momentum addition, these separate sets of angular momentum eigenstates to yield the desired eigenfunctions with angular momentum that is the sum of the two contributions, the spin and the orbital. How this sum must be taken is given by the Clebsch-Gordon coefficients of angular momentum addition. Therefore, in the spherical harmonics basis, this sum is given here, where these are the Clebsch-Gordon coefficients, which are telling you how to add the two sets of angular momentum eigenstates, and we get the spinor spherical harmonics. If one actually carries out the inserts the Clebsch-Gordon coefficients and computes the sum, then the following result is obtained. So the first thing we notice, or the first thing that's important to notice, is that it satisfies these necessary normalization conditions, at least if these spherical harmonics, the scalar spherical harmonics, are normalized properly. Second, this is the result you get straight out of the sum, but we want to write it in terms of the quantum number k, because we've been working with that a lot. So the equivalent version of the spinor spherical harmonics expressed in terms of k is that. Okay, so and it's usually denoted like that. Now the first thing that we notice is up here I said that if one can find a four-component function that is a standard eigenstate of spin and orbital angular momentum, well, we've definitely found a set of functions that are standard eigenstates of spin and orbital angular momentum, but when we compute them, they're two-component functions. And that seems kind of confusing, because we need a four-component one. Because the k operator is a 4 by 4 matrix. But if we look back at the K operator, right there, we see that it's not just a random 4 by 4 matrix. It is one with a very specific form, where on the diagonal there are two 2 by 2 matrices that are the same except for a minus sign. So then we may ask, what happens when we apply this 2 by 2 operator on those spinor spherical harmonics? Well, what we get is that it is an eigenfunction of that operator with specifically this eigenvalue. And if we apply minus the operator to almost the same functions except with minus k plugged in, then we get that it has the same eigenvalue. So then we're looking for eigenfunctions of k, and we need a 4-component function. That means if we take omega plus k comma m and stick that in the top part of a 4-component vector, the 2 components in omega plus km, and then we stick in the bottom 2 entries omega minus km, then we get a 4-component function that does exactly that. And it still makes sense of this whole functions as an eigenstate of both types of angular momentums, and it's still ultimately coming from summing the two together. So it makes perfect sense. And when we do that, we get this result for the angular part. Okay, so we already established what the radial part is, and so we also established the equation is separable, and that the full solution is the product of the radial part times the angular part, which all normalized and everything is this. This is the full solution to the Dirac equation for the hydrogen atom, where, just to remind you, they were given previously in the video, but just to remind you, this g function is that in terms of the asymptotic forms and the associated Laguerre polynomials. Same thing with the f, it's slightly different, but similar. And again, this is the normalization constant, and then this is the definition of the various constants and variables in that expression. And then, of course, just to remind you, that's what the energy formula worked out to be. So that is how you solve the Dirac equation for the hydrogen atom. It's one of the coolest problems out there. D-trick out.